All right, we are entering our first subspace. There are 4 of them. They're awesome. They're great. And this one is called column space. So we've talked about rows and columns, so it's probably got something to do with that, right? But this is all about AX equals B because we are really crazily in love with this little equation. Okay. Well, maybe not. Okay, so let's see. So our beloved problem, or be hated, whatever you like. So I'll put that in as a possibility. Be hated. Delete as applicable. Let's put that down the bottom. I think your feelings will change. All right, so I believe. So problem, AX equals B. So what does this stuff about vector spaces and subspaces mean for this? Well, we know the column picture, right? So the column picture, not to be confused with the picture of column, different thing. So this is x1, a1 plus x2, a2, boom. So let me put the right things here. So this is, okay, let's get it right. This is m by n, always, right? Number of rows, columns. Things have to match up. This is a vector. It's m by 1, and this is m by 1. So glad those letters are very different in the way they sound. Thank you, monks. Let's see, the monks get it wrong. So they're going to be n of these, xn. Really have to concentrate to get this right. So there are n columns. Each column has m entries. Right? Each column has m entries. So it lives in Rm. That's the big deal. So this is equal to B. All right. So the columns of A, so observation of big dealness / big deal. Let's do that. Big deal. Again, mathematical term. Big deal is that the columns of A, the matrix, columns of A, the matrix, and B live in, so this is what we're talking about, they live in Rm, right? If it's 23 dimensions, this is a 23-dimensional space they live in. And we're trying to find a way to combine the x's, or combine the columns of A to make B, right? So this is confusing. So this is not Rn. X lives here. So X lives, it's a sad X. X lives here actually. So we'll get to that next, but X lives in Rn. It's a different space, especially if this is a rectangular matrix, different space. So let's do some examples. Let's see what we're starting to do here. So an example might be A equals 2, 1, 4, 2, right? We're just going to think about A to start with. So you can see clearly, right? So the columns are multiples of each other. Rows are 2, which will make a bigger and bigger deal as we go along. A1 equals 2, 1. A2 equals 4, 2. All right, so let's draw that. Okay, good. Okay, this is something that's very important. So this is actually y1 and y2, right? So the columns of A live in y space. So these live in y space. I'll just say y space as well, right? We've got to use y's there. It will work out. It will be good. Okay, monks told us to do that. All right, so let me say this. So we have, here's our subspace. There is one nice vector here, which is 2, 1. Let's say that's 2 and that's 1, and 4 and 2 here. Right, good. So this one here is, right, so this is A2 equals 4, 2, and then A1 is here, equals 2, 1. Let's put in a zilch, 0 vector is there. So you can see that any combination of these, any linear combination of A1 and A2 will just take you up and down, what have I done? This line. So let's write that. So all linear combinations of A1 and A2, right? Which exactly the column picture, right? i.e. x1 times A1 plus x2 times A2 live on this line. There's no way you can get off it, right? You can't multiply them some way and add them so that they get off this line. And this line, which is a subspace of R2. It's 1D. Right? It's a one-dimensional subspace of R2. It's really awesome. Okay, that's a big deal. It's right, two dimensions. Sorry, so two-dimensional. It's a two-dimensional space. Right? These x's have two entries. They live in general in a two-dimensional space, but these specific vectors and all multiples and all linear combinations of them only live in this one slice. So this is a 1D subspace. We'll get to dimensions a little bit more too, but soon, yeah. 1D subspace of R2. Perfect. Perfectly fine. It has all the properties you want. It has 0 in it. Any two vectors inside it, you add them together, you're still inside the subspace. Any multiple of a vector stay inside the subspace. So that's good. And we can write it like this. We could say, we're going to say, so very important. So notation. So huge. This is huge. CA. C stands for column. So we're doing a good thing here. CA, which equals the column space of A, which very generally is a subspace of, this is something you must get into your head, Rm. And let's denote this again. This is an M by N matrix. And so here, so here in this example, we would say, well, we'll say this, column space of A. Hopefully you can see this, but we have to figure out, given it an A of whatever size, how do we find this column space? Here we can see it. So this is just by, by I. That might be hard to see, by I. This is all Y that live in R2 such that, right, such that that's what that means. Y equals some constant times 2, 1. And C is an element of the real numbers. So that's this is the column space. This thing here is the same as the line, right? It's the same thing. This is set notation, curly braces, very important, and do not deviate from the path. So it's all Y in 2 dimensions such that it can be expressed in this way. All right, so that's huge. This is a definition. Or this is a notation, right? So this is notation. Let me say this. So this is notation. And here we have this. Here's the big deal. Huge deal. No, you were just like, what? This is the best. This is the best. There are more things. It's amazing, 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 amazing. Ax equals b only has a solution right? So AX equals B only has a solution if we come back to this one and I think about this, right? So we're trying to solve AX equals B. What we've shown here is this is where A's columns, when taken as linear combinations of A's columns, this is where they can go, right? So we can't get out here or out here. We can only get to things that are on that line. So B has to live in the column space of A for AX equals B to have a solution. There could be one solution or infinitely many solutions, but that's the rule. All right, that's the story. So hopefully we can start to see this. So AX equals B has a solution. I know you're psyched. One, right? It could be a solution. One or infinitely many. Only if B, so this is powerful. B is in the column space of A. Right? This says B lives in the column space of A. I'm just so happy. Wow, this stuff's the best, isn't it? Right? Has to be true. And so consequently, right, so if B is not, so therefore, right, so it implies that if B is not in the column space of A, AX equals B has no solution. And what we'll do later on is we'll get our best solution for that. We're not sad. We're not sad. This will be okay. This will be okay. So just, yeah. So this is a big deal here. Big deal. So in our example, so for A equals 2, 1, 4, 2, right? So B equals 38, 19. So we really just need that the first entry is 2 times the second entry. That's in the column space of A. So in fact, it has infinitely many solutions because we'll get to it, but there are, because the columns are redundant, right? So you can go past this solution and go past B and come back, and go the other way and come back. We'll get to that. But B equals, say, 1, 0 is not. So I want to say, so right at this point we can say, so no solution. So no solution to AX equals B. And in fact, we'll see for this case, we'll see this means that there are infinitely many. Solutions. All right? Pretty awesome. So we're just doing simple ones, and so you can imagine it gets harder as they get bigger, but I can kind of lay out examples without, because we're in 2 dimensions, not so bad. So another example might be A equals 2, 1, 1, 2. So here are the columns. Right, column 1, column 2, A1, A2. So just, at least at this point, just think about how these look. Again, we've got Y's, Y2, and these ones are, say, right, so this is 2, 1, this is A1, and this is 1, 2. And the question we're really asking is, can some linear combination of these 2 vectors reach any vector in R2? I'm actually going to write R2. That's a notation people use a little bit. I would like to use it. So if we have B here, it's a sad B. If we have B here, can we reach it? So we have to show this, but hopefully you can see that there's some way of multiplying these things, right? And then adding them together, you know, we could work our way up here. And then this one is parallel to this, so maybe something like this. So we could, some multiple of A2, some multiple of A1, we could make B. And so we can sort of see what's happening. It's just 2 dimensions. They're not pointing in the same direction. We can fill all of space with linear combinations of these, right? So we can see, again, still a simple example, see that ax equals b always has a solution. Always has a solution, and in fact, it's unique, right? So in fact, there is only one. Only one. So you can't, right, there's no other way to get to B once we figured it out. So a useful thing to think about here is just I hat and j hat, right? Just in 2 dimensions, or 0, 1, 1, 0, 0, 1. That's underlying everything we do, and it's what we call a basis, which we'll come to again. And we can reach every point, but there's only one representation, right? There's only one way to represent this vector here. We go up, we go across. We can't multiply, we don't have different representations. It's useful to have different representations of vectors sometimes. That's something that will happen. You'll understand which matrices do that. And sometimes we don't have enough representations. That's also extremely common. Okay, so this one could get everything. So you'd say, in this case, we'd say, this is what we get to. CA equals R2. The column space is equal to R2. You can't get a B outside of R2. Right. Another example. And again, we're going to have to figure out a method for doing this, right? We have to figure out a method for understanding, for extracting column space. Some big messy matrix. We need to know what's going on. So 2 columns, 3 dimensions. So these are 2 vectors in 3 dimensions. They're different, right? You can actually see this is really I hat and j hat if you use that notation. So what does that mean? We can actually just only make, right, we're at the edge of our ability to this is in fact y1, y2, y3. We can only make the plane. Plane equals the column space of A in this case. Right, the xy plane, right? So the horizontal plane equals the column space of A. So B is here. Solution. So this is okay. B is pointing up or down in any way. No solution. That's what I'm, right? So we get some sense. We only had 2 vectors, 3 dimensions. There's no way we can get to everything. Okay, that's good. So what about something like this? Another example would be, so that was a taller rectangle. So this is tall. And I'll just put in the next slide. So a tall one. Yeah, another example would be a wide A. And let's say we just have 1, 0, 0, 1, 1, 1, 2, 1. Right, so this is a 2 by 4, M by N. So we think about the columns here, the columns of this thing. Now we've got 4 vectors in 2 dimensions. Now that doesn't mean it's going to work. I think I need to get to a chiropractor. Y1, Y2. Let's draw in these. I'll just draw them in order. So there's a 1, 0. There is a 0, 1, a 1, 1, and then a 2, 1. So this is 1, 2, and 1. And these are A1, A2, A3, and A4. Okay. So can we reach every B with this linear, with some combination of these, right? So maybe B is here. It should be clear that that's okay, right? We only just need the first two vectors. We could see any two of these vectors will work. So we can see, any two column vectors. Vectors of A will work. So will work. Again, we have to just find a way to do this mathematically, but we can sort of see that, right? So some linear combination of any of these two vectors will work, and that means there are more ways than one to do it, and we know that there will be infinitely many solutions. This will be more clear soon, but again, we have a situation where the column space of A is equal to R2, right? The ambient space where this is, yeah. So this is M. This M equals 2. So the picture that's starting to emerge is that this will fill in with this big picture we're trying to get to. So this is the emerging picture. It's going to be a little messy to start with, but we know this is what's going on. So we have x1 down to xn. That's our vector x, and ax equals b, right? So we're trying to get, so b is here, b1. It goes down to b m, which is, yep. So this gets sent to b, hopefully, maybe, ax equals b. And that's okay if b lives in, well, let's see, what does x live in? So x lives in, this is Rn, right? So make a big ball here, so Rn. So x is some point here, b is some point, some vector. And then over here, this is Rm. And inside that, and it could be the whole thing, as we've said, inside that potentially is the column space. Sorry, B may be in the column space, maybe outside of it. The column space may be all of Rm, it may be contained within it, right? So for this example, the column space of A is equal to Rm, which is just R2. In this example, the column space of A is just the plane. It doesn't get all of 3 dimensions. Yeah, so maybe I should add that. So we could say, so here the column space of A is not equal to R3. And again, this is the crucial thing here. This is M equals 3. I should make that here. This is a 2 by A is a 2 is a A is a 3 by 2. M by N. Exciting. Back at this example, we have that A's vectors could be combined to reach anything. So that's a case where the column space of A is equal to R squared, which is Rm. The first example we started with is not enough, right? So again, it's not enough. Column space is smaller than all of Rm. So this is huge. This picture will get much more concretized, right? But it's this is a subspace. The thing about this is that this is a subspace of Rm. And if B is in that subspace, there is a solution. There may be infinitely many. There may be one solution. If it's outside of it, there are 0 solutions. And that's this statement here. Okay, so we're on our way. We're on our way. Next thing is null space. And we'll start to develop methods for figuring out what null space is, what column space is. Obviously, I have to explain what null space is. There will eventually be 3 methods for column space. And it's important they're quite different. It's important for understanding. We'll see one is kind of the best, for many things we do, but they're all important for understanding, but it takes a little while to get to the one that's most awesome. All right, so just slowly get this in. This is huge, huge. First subspace, what a great day. What a great day. Oh my God, I didn't record it. Really?